the side view of the dam, and the water behind it is of depth d. Hydrostatic pressure is going to be a function of the depth, and so now you have the hydrostatic pressure P given as rho g h, where h is this distance from the surface of the water. Because now your hydrostatic pressure is no longer constant, you cannot just simply take P times A to find the overall force on the dam. Instead, what you need to do is take an integral, where now the total force on the dam is the integral of the pressure dA. The next question now we need to ask is, what is this dA? Now we look at cross section of area of this dam. This is the cross section where the force is going to be exerted on. Now in this case we're assuming just a regular geometry, a rectangle, and so let's assume that the channel or the dam is of width W. So in this case dA is simply W times dz, which is dz is this small little strip along this cross section. We're going to replace dA within that and replace P with rho gh. We end up with this integral. W is a constant, so we're going to pull that out. Now all we need to do is to rewrite our h in terms of z, and hopefully you can see that based on how we have defined z equals to 0 as the bottom of the river, we see that h is essentially just d minus z. So to get the overall force, we're going to do this integral from all the way from the bottom, z equals to 0, to the surface of the water, z equals to d. And right now I would like you to press the pause button and try out this integral. We'll come back and you can check your answer. Alright, we are back. Hopefully you had a chance to try out an integration and it's simple enough. Just a recap, this is the final equation that we had from before, and we are going to do the integration, evaluate it from 0 to d, and this should be the final answer for the force. So this is the total force exerted on the dam due to this hydrostatic pressure that is varying with depth. So what we have done so far is considered a regular geometry of the cross section. Unfortunately, life is not as beautiful. Things are not as regular as we want them to be. So let's look at the case where what happens if the cross-sectional is not uniform. For example, in this case, so the force is still the same equation. It's still the integral of pressure dA, and pressure is still this rho gh, this hydrostatic pressure. So we have this equation, and now what we're going to do some math here. And the reason why I'm doing this is because we're going to define that term in that circle as the depth of centroid of surface, or HC. So think about this as the average depth of this, where the center or the geometric center is of this irregular cross section. So if we simplify this now, our force has a much more simplified equation, and the integral is in this HC term. So let's now look back at our regular geometry to make sure that we still get the same solution that we got before. So let's calculate this depth of centroid, HC, for our regular cross section. In this case, our A is simply just W times D, and H is still D minus Z. Make our substitution for dA as shown here, do the integration, and we get our depth of centroid as half D, which should make sense. The geometric center would be halfway down the depth of this geometry. So putting this back into our force equation, and you see that we do indeed get back our same force that we got from before.